If modeling intertidal elevation using the Digital Earth Africa platform is a topic that you will find interesting, then please do stay tuned for this live session today. Greetings, leaders from the African continent and across the world. It is so exciting to be hosting you today for our very first live session of 2024. I think it's apt that I wish you compliments of the new year, and I hope that it will be a very, very successful year for you. We're very excited about everything that's going to unfold for Digital Earth Africa this year, and especially with the live sessions. We'll talk a bit more about that as the year unfolds, but thank you so much for joining us and for being with us here today. The topic of discussion today is going to be all about modeling intertidal elevation using the Digital Earth Africa platform. I know you're going to find this topic interesting, so let's get started. I'm very excited to be introducing today's presenter. She's no stranger here at Digital Earth Africa platform, and she's not going to be for most of the year. She is the Digital Earth Africa Earth Observation Data Scientist. Please join me in welcoming onto the virtual stage my fellow colleague, Mpho Sadiki. Mpho, the virtual stage is yours. Over to you.
Thank you, Maud. Good day, everyone, and thank you for having me once again. I'm very happy to be the first one to present this year. So thank you for joining us for our first live session in 2024. And as Maud mentioned, my name is Mpho Sadiki, and I'm an Earth Observation Data Scientist for Digital Earth Africa. And today I'll be taking you through modeling intertidal elevation using the elevation data within the Digital Earth Africa platform to remind everyone and to let everyone know who is new to the Digital Earth Africa platform. Everything that we'll be doing today is in the Digital Earth Africa Analysis Sandbox. So this is a cloud-based computational platform that operates through a Jupyter Lab environment, and it gives you free but is also limited compute resources for you to be able to explore and interface with the Digital Earth Africa data cube. So the two notebooks of interest today are the Intertidal Elevation Notebook and the Intertidal Elevation Notebook Sentinel-2. So they are two notebooks that are very similar. The difference is that one uses Landsat data, which is the intertidal elevation, and the second one with the S2 uses Sentinel-2 data. And as you already know, all of our notebooks are available on GitHub, and they're already preloaded onto the Digital Earth Africa Sandbox. So if you are already registered on the Sandbox, you should be able to access these in the Real World Examples folder. And if you're not already registered for the Sandbox, please head on to sandbox.digitalearth.africa and create your account and get working with the Digital Earth Africa data, and also try and follow what we did here in this live session. So now on to today's business. Before we go into the notebooks, I'll just like to give you a bit of an overview of what intertidal elevation is, specifically the intertidal zone. So as you probably already know, because of the moon, the sun, and the gravity, the place where the Earth meets the ocean is not a static line. So it's not a fixed line as we usually see on maps, where we usually represent the mean sea level, but rather it is a zone that is always shifting depending on whether there's a high tide or a low tide. And that is called the intertidal zone. So this is the area where the ocean meets the land in low tides. And if it's a high tide, it's covered in water, but it is exposed to the air at low tide. So this area can include many different types of habitats, which include steep rocky cliffs, sandy beaches, and wetlands, amongst others. And there are 4 physical divisions that divide this intertidal zone. We have the spray zone, which is dampened by the ocean spray and high waves and is only submerged during very high tide. So that is the area, if you look at this image at the bottom here, at the very top of the zone. We also have the high intertidal zone, which is the second zone here. And this zone floods during the peaks of the daily high tides, but it remains dry for most of the high tides. And then we have the middle intertidal zone, where this is where tides ebb and flow around twice a day, and it's usually inhabited by a variety of plants and animals, which include sea stars. And then we have the low intertidal zone. This is at the very bottom there. This is virtually always underwater, except during the lowest tide in spring. And life is more abundant there because of the protection provided by the water. So the intertidal zone faces increasing threats due to a number of reasons, which include coastal erosion, land reclamation, such as the construction of ports and the rising sea levels. So accurate data or elevation data that describes the height, the shape of this coastline is needed to help us predict when and where these threats will have the greatest impact. However, this is very expensive and challenging to map and across the entire intertidal zone of a continent as big as Africa. But you can reveal rather the three-dimensional shape of the coastline by mapping the boundary between the water and the land across a range of known tides. And that's what we'll be able to do today. This is assuming that the land-water boundary is a constant line relative to the mean sea level, and you can then model elevations for the area of coastline located between the lowest and the highest observed tide. So you can use imagery from satellite imagery from satellites. And as I mentioned earlier, we have two notebooks that do that. We use the NASA Landsat data, and that's what we will show in this example, but there's also an example that uses the ESA Sentinel-2 data to model the intertidal elevation. So as I said in the very beginning, we'll show a simplified version of the National Intertidal Digital Elevation Model. So this is a modeling method that was developed by Bishop Taylor et al. 2019, and they did that to create the first 3D model of Australia's entire coastline. But obviously we've taken that model, we've simplified it, and we've now applied it to the African context. So first it maps the boundary between the water from low to high tide, and it uses this information to generate smooth, continuous 3D elevation maps of the intertidal zone. And the resulting data or the resulting 3D elevation map can be used to map the habitats that are threatened, the habitats of threatened coastal species, identify areas of coastal erosion, and planning for extreme events such as storm surges and flooding, and improving models of how sea level rises will affect the coastline. So in the Digital Earth Africa use case, there are 5 major steps that we will go through in addition to the more traditional ones of specifying the packages that you require for the analysis and specifying the area of interest. You also compute the normalized difference water index, tag and sort the satellite imagery by tide height, create a summary or a composite of images that show the distribution of land and water at discrete intervals of the tidal range, and we'll extract those and visualize the topography of the intertidal zone as contours, and we'll interpolate those contours into a continuous 3D model of the intertidal zone. So these are the steps that you would expect in both notebooks, whether you're using Landsat or Sentinel-2. So before I go to the end, I will actually just go in here and start sharing the notebook. As I said before, this is a notebook that you can find in the real world examples. So if you go into the real world examples in the sandbox and scroll down, you should be able to see 2 notebooks. There's Intertidal Elevation and Intertidal Elevation S2. So the S2 is when you use Sentinel-2 data, but it's exactly the same as using the Intertidal Elevation notebook, the more default one that uses Landsat imagery instead. So before I start going through the notebook, I'll just refresh your minds on how to run the notebook. Each cell, for instance, if I just go down and go to the first one that loads the packages, can be run using this particular icon. So you can select it and run, but you can also just run the entire notebook using this restart kernel, and then run the whole notebook icon. So when you do that, it'll ask you to restart. This will just rerun the entire notebook from the top until the end. And this is not actually a very long notebook, so it doesn't take that long to run. So as do most of our notebooks, we start with the background of the notebook in terms of why it's needed and what it could potentially include in it. So there's just the background that really provided in terms of what intertidal environments are and why it is necessary. And in the description, you can see that we are going to use the National Intertidal Digital Elevation Model method, as I explained, and it will leverage the Landsat 5, 7, and 8 satellites from the Digital Earth Africa data cube. And in the notebook, you will be able to load the cloud-free Landsat time series, compute the NDWI, tag and sort the imagery by tide height, and create summary or composite images that show the distribution of land and water at discrete intervals, and extract and visualize the topography as depth contours, and then interpolate those depth contours into a smooth, continuous elevation, digital elevation model of the intertidal zone. So as we already know, the first thing that you need to do is load the key packages as well as the supporting functions for the analysis. This is pretty standard, and you'll always encounter this when you work with our notebooks. In this notebooks, you also notice that you have to set up a Dusk cluster. So Dusk is a useful tool when you're working with large analyses, either in space or time, because it breaks your data into manageable chunks that can be easily stored in memory. So you can also use it to for multiple computing cores to speed up your computations. So basically it can be used to better manage your memory usage and conduct analyses in parallel. So we actually have a notebook in the beginner's guide of our notebook repository. So if you go out and you go to the beginner's guide, there is a notebook called Parallel Processing with Dusk. So if you want to know more about how to do that, you can actually run that notebook or go through that notebook to understand more of it. Now back to our notebook. So that is how you actually create a local Dusk cluster. And when you do that, it will actually give you this section. And with this link, you can see if you click on it, it will open a different window that you'll be able to see as you're running your code, what the different processes that are running are. And of course, you'd also need to activate and connect to the data cube. This is also very familiar to you by now, I'm sure. And another more familiar step is the analysis parameters. So the analysis parameters, you're setting things like the location and the time that you're interested in. And the way we have it in our code, you have two ways to define your location, which you can pick from. You can either use a latitude, longitude, and a buffer, or if you have a shapefile or a GeoJSON file, you can comment that out and then uncomment the line that allows you to use a shapefile or a GeoJSON to add your data. But in this case, we will be using the latitude and longitude and buffer method. And this area is actually off the coast of Guinea-Bissau. We'll see when we actually plot where the area is a bit later on. And this is a very important line here. It's very important to make sure that when you're using this notebook, the center of your study area is located over water, because we are interested in the intertidal elevation, the areas where the water meets the land. So that's very important. And for this study, or this example, we're interested in the time range from 2014 to 2020. So that's how you would specify your area of interest. And this line of code here just allows you to view your area of interest that you've specified. And this is an interactive map, so you can zoom in, zoom out, and pan in and pan out as you need. Then this will allow you to be more familiar with the area that you are working at. So you can see you can zoom out, zoom in, pan around, and understand the area that you're looking at. So now we move on to loading the cloud masked Landsat data. So this is the first step of the analysis after you have specified your location and your time range, and you've connected to the data cube and all that stuff that I said before. One way to do it is to specify a query, or to specify a query that will allow you to load your data just easier, especially if you want to use it more than one time. This is not always necessary, but it's good practice to always have it, because it is useful if you're going to use it more than one time. So you just specify the X and the Y. This is what specifies the location or the data for you that you want to pull, and the time range. Remember, these are the two parameters that we specified. Yeah. So those are the two that you're adding there for the X and the Y and the time. And the measurements, these are the measurements of the Landsat 5, 7, and 8 that we want. So we want the red, the green, the blue, and the near-infrared band, and we want them at the resolution of 30 meters. So that is how you'd create a reusable query. And to load the data, you're using the load ARD, which is a function to load data, and also does the cloud masking for you as you bring it in. And just a few more parameters that you can specify, which include the minimum amount of good data that you want, the output CRS, and a whole host of other things. So as you can see, the data is loaded, and it counts how many timestamps it was able to get that have minimum amount of good data of 50%, or good pixels rather, and that's 174 out of 280 possible timestamps. So if you print that data that you've loaded, you'll see it has the red band, it has the green, the blue, and the near infrared, and here it'll show the time dimension, and you have 174 of those that cover your area of interest. The next step is the clipping data sets to the shape of the area of interest. This is particularly useful if you have defined your area of interest using a shapefile or a GeoJSON, and you want to continue just for that particular shape of the area of interest. Because as you add it, when it gets the data from the data cube, it uses a geopolygon. So it just gets the extent of, like, a regular shape extent of your area of interest instead of the exact shape that you want. So if you do want to clip it to the exact shape that you loaded with your GeoJSON file or your shapefile, you can use this code to do that. And also, this is just an example of how you can plot an RGB composite of one of the time steps. Remember, we have 174 of those. Plotting all of them would not be, it wouldn't make sense, especially if you just want to visualize what one of them looks like. So here, the 12th time step is selected, and it's plotted or visualized using the RGB utility function, which plots a true color image for that given time step. This is what that looks like. So now on to the 5 steps that I mentioned earlier in the presentation that you need to do to be able to get the intertidal elevation for your area. So the first thing is the computation of the normalized difference water index. So the reason you need to calculate the NDWI is because you need to be able to separate water from land. And those who are already familiar with the formula for the NDWI is the green band minus the near infrared band over the green band plus the near infrared band. And to do that, we actually use one of the functions or the modules that we have in the Digital Earth Africa tools. If you go out to tools, you go into Digital Earth Africa tools and go into calculate indices. There is actually a module that does that, band indices. So that's the module that does that. And this is the function that you use to compute the water index. It has a limited number of indices that you can just call on to compute instead of having to write out the formula yourself. We also have the, I don't actually see it here. Yeah, but that's the function that you'd use to do that. So you just specify that you want to do the normalized difference water index, NDWI index, and the satellite mission is LS. Remember, we're working with the Landsat data set. So that's why you put LS there. And this is what that would look like. Once again, this is just for one time step. This is the time step that we declared here. So this is actually done for all 174 time steps, but we're just showing it just for the one. Thereafter, you need to model the tide heights. So this is, like I said, the location of the coastline varies. It's not just the line. So you need to be able to extract that for each image, each of the 174 images. So what you then need to do with what we're doing rather with this code, we're calculating the height of the tide at the exact moment each Landsat image, each of those 174 Landsat images were acquired. And this will allow us to build a sorted time series of images taken at low tide to high tide, which will be used to then generate the intertidal elevation model. And this uses the tidal tag to calculate the height of the tides at the exact moment the imagery was taken, and it adds this tide M attribute, which is the height of the tide at for that particular image to each data set. And you see that it is added as a data variable there, in addition to the red, the green, the blue, the near infrared, and the NDWI that we just calculated above. So now that we modeled the heights, you can actually just visualize them to see the range of the tides that were captured across the time series. So from 2014 to, I believe, 2020. So this is, it shows 2021 there, but that's the end of 2020, so December 2020. So now that we have the tide heights, we can sort them, or rather sort the Landsat data sets by tide height, so we can reveal which parts of the landscape are inundated or exposed from low to high tide. So because individual imagery can be affected by clouds, sunlight, or poor water quality conditions, it's important that you produce cleaner images that can be compared easily between tidal stages. And that's why we create summaries or composites that combine multiple images into one. It's like creating a median of the landscape at different tidal stages. So in this case, we use the median as the summary statistic. So we are creating medians of imagery. Because it prevents strong outliers from skewing the data, which can be useful, which would not be useful if we were to use the mean. So in this code here, we take the series of images and we sort them by tide, and we categorize them into 9 distinct intervals of tidal intervals, rather, ranging from the lowest tide, which is a 1, and then to the highest tide observed by the imagery, which is interval 9. So that's what this code does. And you can see the tide interval is added then as a data variable into our data set. We can then also plot, once again, the boundaries between the 9 tidal intervals on the plot we generated earlier. So you can see that here. And now that we have a data set where each image is classified into a discrete range of tide, we can combine the images into a set of 9 individual images that show where water is located from low to high tide. And this can take a bit of time. So that's where the dusk processing actually comes in. It can help you speed up this process. And that is done by this code. And we can actually see the plot here that clearly shows the shape of the structure of the coastline changing significantly from low to high tide as low-lying tidal flats are quickly inundated by increasing water levels. Thereafter, we would want to then extract an accurate boundary between land and water for each tidal interval above. So for all of these 9 intervals here, we want to extract the accurate boundary between land and water. And this is the code that does that. It identifies the depth of the contours based on the boundary between water and land by tracing a line along those pixels with a water value of 0. So that's where you sort of like a cutoff between water and land. And we can see that happening here. So this is just a visualization of the depth contours. So deeper contours, these are in the yellow colors, and the more shallow ones are the red contours. You can also plot these contours on an interactive map. So you can zoom in, zoom out, and also pan and just explore those contours for yourself. Okay, so now we have the contours, and they do give us information about the topography of the intertidal zone. But we can also extract some additional information by actually creating a 3D structure of the coastline. So we convert these into a digital elevation model. And this is done using this code, where you convert the shapefile. Remember, these are lines, so they're vector lines, a shapefile. You convert those vector lines into an array of points with an X, a Y, and a Z coordinate, where the Z coordinate is rather related to the elevation relative to the mean sea level. And we use those to create continuous elevations across the intertidal zone using a linear interpolation. And this is the resulting output, but you can see that this covers more than what these lines actually cover. And this is because the interpolation extended across the entire study area, so it didn't just restrict itself to the intertidal zone, but that's not a problem at all. We can clean it up by restricting it to just that DEM, to restrict it to where the area between the lowest and the highest tides were observed, and that will then actually just give you your intertidal zone instead of the entire study area. You can also just, as you run it, you can import this, or rather export this intertidal DEM as a GeoTIFF that you can then open in QGIS, ArcGIS, or whatever GIS software you use. For instance, using QGIS, you can just go there and explore it outside of the sandbox. So that is all for this notebook. That was quite a bit to go through, but just to ease your minds as well, I'll just open the Sentinel-2 one to show you that it's exactly the same as the one I just went through. The only difference would be obviously the time range, because Sentinel-2 in our data cube goes from 2017, so you wouldn't be able to go back in time to the 1980s. And you would also change the resolution and load Sentinel-2 instead of the Landsat 5, 7, and 8. But that's the only difference. Everything else sort of remains the same. You go through the same process that we went through now. So please bear that in mind should you be interested in doing this for Sentinel-2 instead of Landsat. Now I'll just go back to my presentation. So we've gone through that, but before I leave, I just want to remind you that we have Digital Earth Africa training courses that you can sign up for. You can enroll into the Intro to the Sandbox, the masterclass. We also have self-paced, free to access fully online videos, tutorials, and manuals that will give you some experience with working with the Digital Earth Africa platform. And for some of them, you can actually get a certificate of completion upon completing the exercises. And so if you want to access all of that, please head on to learn.digitalearthafrica.org. You can also email at training@digitalearthafrica.org. And you can also go to our website to learn more about us. And we also have a help desk where you can that you can subscribe to, and you can receive quarterly newsletters and invitations to attend events. And please remember, this might be the first one, but we have them every week, the Digital Earth Africa weekly live sessions. This week was in English, but next week the same information will be reiterated in French for our French community. And you can also email Digital Earth Africa at info@digitalearthafrica.org. Thank you very much. That is all for me.
Thank you so much to you, Mpho, for that very elaborate presentation. I definitely learned something new today. This notebook, ladies and gentlemen, is accessible via the Real World Examples tab. Correct me if I'm wrong, Mpho. Real World Examples tab in the sandbox. We're going to drop a link to the sandbox in both the chat box and in the description. If you're not registered as a sandbox user, head on to sandbox.digitalearth.africa, register a profile, and you'll be able to access the sandbox at any time. And the one that's specific to today's topic, which is all about measuring intertidal elevation, is the notebook that is called Real World Examples, and you'll be able to find the information there. But thank you so much to you, Mpho, as always, a stellar presentation, and we absolutely love hearing from you. We'll see you again next week if you prefer a French session, but if not, we'll join again in 2 weeks' time for the next one. Until then, please take care, leaders, and be safe, and thank you so much for joining us for today's live session.